moment diagrams ready. I hope you've done it. Okay, morning. Let's see how many are in. 46, 45 of you are in. I think we shall give the latecomers maybe another 5 minutes, and then we will start. But meanwhile, I think by 8, I think all of you can scan your attendance. Now, please try to remember to scan your attendance because all these are online. It's already all automated, so it's not like the good old times where you know we have to key in one by one for you. But now it's all automated. So please, once you scan, please check to make sure that your name is marked as attended. Okay. So for today, what we are basically going to cover, or I will try to cover the next 2 hours, is the remaining of the examples on moment distribution for beams. And then we will also, in the second half of the hour, we will try to cover the frames without any sway. Okay. So hopefully by the end of this week, we can cover moment distribution so that you can actually also start with your assignment. Okay. The next week, just to remind you, something big is happening next week. It is your midterm test. It will be held on the 3rd of August. Please don't forget, it starts as early as 8 o'clock, 8 a.m. sharp. So for those who are night owls, OWLS, night owls, please try not to be a night owl, okay? Get up early, have a good breakfast, and then download the questions so that you can start at 8 o'clock, okay? Dr. Woon and I, we will be on standby. So if you have any problems, cannot download or whatever, but I believe all of you by now, you're already in year 2, you should be quite familiar with the system of uploading, downloading, and stuff like that from Webble. Now, for those of you who do not have, please quickly go and ask your friends or refer to the handouts. I believe that our faculty office has sent out through the email. Okay, so please do so. And in any case, I think for your assignments, you have enough exposure as to how to upload and download the files. Okay, so I do not expect any of you to have any problems in that area. Okay, what else do I need to talk to you about today? Okay, I think that's about it. Now, so anyway, we will just do a quick recap. So far, we have done moment distribution. I've introduced to you moment distribution. How do you apply this analytical method to beams, continuous beams? beams that are fixed at the far end, right? So we will, and then after that, from the internal moments that we get from the analysis, what we do is we will plot out the shear force and bending moment diagram. Okay, so your cost, in fact, for this entire essay 2 is up to drawing the moments and shear force diagrams. And then later in your third year, after if you pass, when you pass this course, you will be going to the design class where you will be extracting all these shear force and bending moment values, and you will take those values to design the elements itself. You will be designing the beams, you'll be designing the columns, you'll be designing the slabs, you know. So this is this course is purely analysis. Okay, the subsequent courses will be design. So some of you may find it a little bit dry here. Yeah, I mean it is a bit dry. It's kind of boring. You don't see how these will be relevant to you, but believe me, they are relevant, especially this topic. Okay, especially when you do not have your design softwares with you, you know, internet is down and things like that, so your computers are not working, so you will have to rely on the first principles and on your hand calculation. So this particular method is a very powerful method for you to get the internal moments and henceforth the shear and bending moment diagrams. Okay, so that being said, so let's start. So remember last week we went through this example 2 where you had a 2-span beam, right, fixed at A and fixed at B. So what you have here is you use the moment distribution where you determine the member stiffness at every end of the span. So end A, end B, and C. Okay, all the 3 ends. You first determine the member stiffness, followed by distributing it according to the stiffnesses. Right, the stiffer the member, it will attract more. You will find that the stiffer the member, the factor that you need to use will be higher. And then determine the fixed end moments if there are any loads acting along the member itself or acting on the member itself, because we are basically looking at joints only. Okay, we transfer every load, every applied load to the individual joints of each member, and that is how we actually do the analysis. Because once we take the moments that we put it to the joints, and then we start to distribute to each and every member that is connected to the joint, it's what we call a relaxation method. So you wind up a spring, you let it go, and then you wind it up again, you let it go until the whole thing balances out. Okay, that's basically the general concept of it. So after that, we managed to get the internal moments. The last line here, okay, this line, a summation of M, basically it summarizes all the internal loads at joint A, joint B, and joint C, or rather at the ends of AB, BA, BC, and CB. Okay, so with these internal moments, and for those who were not awake during the last lecture, please change this value to 10.4. Actually, it should be 8 plus 2.4. Okay, then after that, what we did is we calculated all the end shears. Okay, all the shears at the ends of each member, the black arrows here. So from here, once we have the end shears, you can then actually plot your shear force and bending moment diagram. So for those who have done, I hope you have done it. Oops, sorry. So if you look at this, right, you have a shear at the end of 1.6 kilonewton downwards. This one is 1.6, and there are no loads here. So when there are no loads here, what your your diagram for the shear force would be, it is going down, right? Negative 1.6. It will be a straight line back up to 1.6. Now, if you look at this, this is 10.2 now, right? This is the shear at the end of BA. So 10.2, here you have 1.6. So you take another one, which is 10.2. Okay, so the total here is 10.2. So that the total you will get is 11.8. Okay, that would be the reaction. Now, you have a uniformly distributed load. You know that this one, as we go, you'll be going down this way, and then finally you have a 13.8. Now, all these you have already learned in your SA1. I think Dr. Woon has done a very good job in teaching you how to draw this. Okay, so then for bending moment, now this, you need to also remember your the relationship between M and V. So the moment is normally, so remember you have your moment is normally the integration. Okay, or if you want, you say the gradient of the moment, that the gradient of the moment is equal to your V. Okay, so here if you look at this, the gradient, the V, the value of V here is negative. So obviously you know that this portion here, your gradient will be negative. Okay, so if you look at your internal moments here, here, and here, you will find that your moment is actually this way. Okay, this is positive 1.6 because your moment is 1.6 kilonewton meter. Oops, sorry, forgot this is. Okay, and here, this one, the area under the oops, what happened? The area under the curve of this shear force diagram would be your moment. So you take the area, you should be able to find what is this value. You'll find that it's also here. Okay, 3.2. And then here, because oops, sorry. And here, this is your V, right? So the gradient of M is your V. So this is positive here. So which means the gradient, oops, sorry, let me draw this line. Okay, so the gradient here should be positive, and then when your V is 0, this is 0 here, right? This would be the turning point, and this turning point is your, this is when your dm by dx is equal to 0. So then you will have 5.47 here. And here, this is the last one, which is 10.4. Okay, so I hope most of you have this diagram. If you don't, if you still find difficulty, you can either ask any one of us, either Dr. Woon or your own tutor, those of you in Ms. Lam's group, or those of you in my group. Okay, it's really up to you, but you really need to know how to draw this. So for those of you who are still struggling with drawing of shear force and bending moment diagrams, please try to either consult your friends or consult one of us. Okay. Alternatively, if you cannot get this diagram, you may either email to me or through the chat here on Microsoft Teams. Send it to me, show me your working, and I will tell you where you go wrong. Okay, sometimes it's better that you show me where, you know, what you have done. Then I will tell you where you go wrong. Okay, then you will not repeat the mistake again in your FA or in your exams or even in subsequent problem solving. Okay, so with that, we will go on now to the next example. this is a new one. Okay, we will be running through examples, and then after that we will go to the rings. Okay, so example 3, consider a beam ABC such that joint A is fixed and joints B and C are on rollers. So if you were to just draw, I mean, in exam, you can also draw it this way. Roller and roller. So you have A, you have B, and you have C. And and these are your loads. Okay, so you can draw it this way, or you really want this, because this one I extracted it from the book. Okay, so you can either draw a line diagram like that or this way. It's really up to you. Okay, so when you have pin, we will draw like that. When we have rollers, we draw like that. When it is fixed, we draw like that. So these are very simple symbols that you can actually use it to draw your diagrams. Okay, so if this is fixed, these are roller and roller. So how are we going to find the internal moments in the beam? So the internal moments that we are talking about would be this. MAB. Now I'm following the same sign convention. Okay, this is MBA. This is MBC. And of course, this is MCB. Oh. Now, as you know, this is a roller. If this is a roller, there is no moment here. So this one, you know, definitely is 0. You don't need to even consider anything. Now, this is a roller, but the moments here are not 0 because these are internal rollers. They are not end rollers. They are the internal rollers. So they will have moments, because why? When the load is acting on the beam, there will be some form of rotation here. Okay. Maybe I will draw a little bit exaggerated. It will be something like this. So this would be your deflected shape. Now the deflected shape or the deflected curve normally will show you the shape of your bending moment diagram. That's why some school of thought, they will use this deflected shape to be the same diagram as the bending moment diagram. Okay. But this is just the deflected shape. It's not the bending moment diagram itself. Okay. So here, your task is actually to find all the internal moments. So here you have already found one. Very simple. You don't even need to, you know, in fact, the minute you see this, you know that this is 0. So you don't even have an MCB. Okay. So to use the bending moment, to use the moment distribution method, the first one that we need to find is your member stiffness factor. Now, if you recall, we had our member stiffness factor, we had either 4EI over L or 3EI over L. Okay, this or this. This was for fixed ends. This was for pinned or rollers. Okay, so sorry, far end. Don't forget, it's not the internal. Far end. The far end is fixed. Far end is pin or roller. So if you recall if you look at your diagram, right? I will just draw the diagram here again for you. This is your diagram. If you look at member AB, right? Internal, we always assume them as fixed. Okay, we don't care. We just take it as fixed because we know there are internal moments. So look at the far end here. Far end is fixed. So we are going to apply 4EI over L for AB and BA. Okay, so you see 4EI over L. For BC, this is the far end, right? This is the last, sorry, this is the far end. So this is pin or roller. So when I stand here, okay, this is my far end. So this is a pin or roller. So when I'm looking for KBC, I will apply 3 EI over L. Okay, I will apply 3 EI over L because this far end is P. Now, on the other hand, if I were another guy, if I stand here now and I look inside, this is the far end. So the far end here is fixed. So that is why for KCB, I use 4 EI over L. Okay, so these are the, in fact, these two are the main member stiffness that you really have to remember. Don't remember anything, but this is very important. Okay, so once we have established the member stiffnesses, then what do? We will establish how much of these moments, right, will be distributed to each and every member. So we establish the distribution factor. And if you recall, your distribution factor is the ratio of the stiffness of the member divided by the sum of all the members, right? Sum of all the members, n to n, maybe just summation of kn. So sum of all the members that are connected to the joint. Okay, so in this case, the first letter here represents the joint connection. This represents the joint. Okay, so this is joint B. We are talking about joint B here, and this one we are talking about joint C. Okay, so all this, the first letter always represents the joint. So if I look at AB, remember that day I told you guys, if you're looking at joint A, in this case, joint A is like that. So when I'm looking at joint A, the two so-called members would be, one is a wall, and the other one is your the other one is your beam AB. Okay, so here I will take, if I'm saying AB, then I'm taking the K of A here, K of AB here, divided by the sum of all the stiffnesses that are joined to the node A. So I have KAB here, and this is the K of the wall. So the K of the wall, I assume it to be very stiff. So anything divided by infinity is actually 0. So that is how I establish my distribution factor at AB. So likewise for BA, now if I look at BA, if I'm looking at joint B now, I have B, I have A, and I have C here. Okay, so I have actually two members, BA and BC. So when I take the distribution factor, I will take, when I'm at BA, I will take KBA here, and I will divide by the two stiffnesses of the members, BA and BC. Okay, so likewise with BC, this is actually, if you don't want to use this method, you can use this. You can take KBC divided by KBC plus KBA. Okay, you will still arrive to this. Now the reason why we put 1 is because you know that this is a ratio. So if you add up all the stiffnesses, it should be equal to 1, right? The ratio should be 1. So you just take 1 minus that, you should get the remaining distribution factor for the remaining member. So then for CB now, if you look at your connection at C, C is here, this is a roller, right? And this is CB. So this is CB. So this is KCB. And here is the stiffness of a roller. Now, the stiffness of a roller is not stiff at all. It can rotate. So that's why the stiffness, we assume it to be 0. Okay, so this one you will get your distribution factor as well. Okay, this is just a recap of the previous lecture of how we arrived to the distribution factor. So some of you, if you have already understood all this, so bear with me, because when I go through the lecture, it is meant for the majority of the class. All right. So those of you who are much faster, you already understand this. Just bear with me for a while. Okay. Okay, fixed end moments. The only fixed end moment we have is on BC because that's the only span with the applied load. So in this case, same thing. If you look at BC here, B was like that, C was like that. Of course, you have A. So your load was here. So remember, we said here we will assume it to be fixed. So if you look at your fixed end moment table, you should be referring to this. And when you refer to this, what you have here would be WL squared by 8. Now, if you look at our sign convention, we say that clockwise is positive. So because this is positive clockwise and this is anti-clockwise, so we introduce. How do I get rid of this? Do I get rid of this? Okay. Anyone, how do I get rid of this? Oh, okay, never mind. Oh, okay. So what you have is negative. We introduce a negative here. Okay. So then after that, we will establish our moment distribution table. As I mentioned earlier, the first line, you will indicate all your joints. So in this member, you have 3 joints. Then you look at the member itself. Okay, sorry, the beam has 3 joints. Then you look at individual member. Joint A is member AB. Joint B, you have member BA and BC. Joint C, you have member CB. So these are the members along the whole structure. Then this is the distribution factor which you established earlier. At the wall is 0, at the roller is 1. Then these are the 2 ratios. If you add them together, you should get 1 because it is summation of distribution factors at each joint is always 1. Okay. Then you establish your fixed end moment, which you got here. You put it into under BC. Now, same thing. A is fixed, right? So you don't need to release any moment because it is fixed. You're not going to change the fixity, so you don't release the moment here. Here, okay, I forgot. Here is release moments. Okay, I'll release your joints. Release joint. Okay, so then you look at joint B. Joint B was what we did was we fixed it to get all the fixed end moments here. So what we do is now we release it. When you release your joint B, what happens? When you release your joint B, this is joint B, you have this moment here, which was this way. I think I will put like that, so that, or for those more advanced one, you can actually establish it like that. Okay, it's either this or this, it doesn't matter. So the minute you release B, right, you should get an equal and opposite. So I will put equal and opposite, equal and opposite. Here I will put equal and opposite, 12. Okay, so that's why sometimes I prefer to get rid of the negative. It's easier. So this is your unbalanced moment. And this unbalanced moment, you need to distribute to the members here. Use your distribution factor to get this. Okay, so this one is actually 0.47 multiplied by 12. Now, here, why do we not have a negative? Because you remember I told you, you will have an equal and opposite moment. So this is negative 12, equal and opposite would be 12. So here I have 0.47 multiplied by 12, I should get 5.64. Okay, so this is how you get your distributed moment. So when we say distribution, means we are actually distributing it. We release and we distribute the moments. Now remember, the other thing that we need to look at was our carryover factor. This only applies if the far end is fixed. If the far end is pin or roller, we don't apply at all. So in this case, the only far end that is fixed from B to A, this is your far end A. So you transfer 50% here. Okay, You carry over 50%. Now you look at BC, C is actually not fixed. So here you don't carry over. So here there is no carryover factor. Okay, here, down here. So with that, now you look at all your joints. You have 2.82, nothing, nothing, nothing. So the next step by right, you should release your joints again to see any unbalanced moment. But because there are no more unbalanced moment, you can now add up like that. This is how you add up. You add up from the FEM line, just add up all the moments. Okay? So with that, then you have all the internal moments here, 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 and here, which you can transfer now because why? You need to establish your end shears. Okay? You need to establish this. You need to establish this. You need to establish this and this so that you can draw your diagrams out. Okay? So here is your internal moment. Look at this. This is positive. That's why I maintain the positive sign here. This is clockwise. 5.64, it is also in the clockwise. Now look at 5.64 here on BC. This is BC. Sorry, I forgot to write here B. This is BC. This is B. This is A. Okay. So this is C. So BC, you have 5.64, but because this is negative, you know that it is in the anti-clockwise direction. So that's why I draw it this way. Okay, I turn the arrow to the anti-clockwise direction so that I get 5.64 in the anti-clockwise. And here was 0, so there's nothing. Okay, so this is how you establish your internal moments. Then next, you take member by member, member AB, calculate what is summation, calculate what is AY, calculate what is the shear on the left of B. You just have to use your summation of moment about joints, about A equal to 0, then you should be able to get your BBL. You take summation of M about your B equal to 0, you should get your AY. Or if once you have done that, you can also go to summation F1 equal to 0. Okay? Here, all the free body diagrams, you can use your summation Fy equals 0 or summation M sec equals to 0. Okay? So these are these are all the equilibrium. These are already determinate. You can actually just use your equilibrium equations. Okay? So this is the bending moment and shear force diagram, which I have plotted out for you. Now, for those of you, go back and please try how to draw this bending moment and shear force diagram. Okay. Any questions so far? These are relatively simple examples. I just want to get you, I just want you to get into the hang of analyzing it, feeling comfortable with releasing the joints. Okay, then if no questions, let me proceed on to the next example. I'm expanding it to 3 spans now, but again, I still maintain the far end fix just for your practice. This one is again same thing. You are asked to determine the internal moments at each support of the beam. Each support, that means A, B, C, D, all the supports. And you take EI as constant, which means this is a prismatic structure. Okay, uniform cross section. Okay, so the first step, you establish member stiffness factors. Okay, establish our member stiffness factors and the distributed joint factors. So here again, you look at your each and every member, A, B, B, C, and C, D. And then you establish, is it 4 EI or 3 EI? So in this case, all are 4 EI over L. And then you look at your distribution factor as we established earlier. Those that are at the wall, your distribution factor is 0. And then you look at your distribution factor for BA. BA is joint B has 2 members, so therefore you will need to sum up member BA and BC. Okay, then for CB again, same thing, you need to sum up member CB and BC. And for member CD, C to D, you have also I don't know, you can call this P if you want. Okay, so what he has done is, CD. Okay, CD is C to D, D to C. Okay, C to D, D to C. And then of course, here we already established here, BC. Okay, so once you have found the member stiffness factors and the distribution factors, you go on to find the fixed end moments. Fixed end moments, if you look at this, you will find that there are no fixed end moments at joint member AB. Then here you will have uniformly distributed load, and this one you have a point load that is in the middle of the span. So what you do is you go to your table, and they are all fixed. So you go to your table to find this. This is W, this is L, so this is WL squared by 12. The other one, where you have the point load, you need to look for this. Now remember your point load, there are 2. One is where the point load is not equal. So in this case, I think they put L by 2. Okay, so this is P. So again, you read this, this is PL by 8, this is PL by 8. So these are the 2 diagrams that you should look for in your fixed end moment table. So please, during exam, don't be so careless, okay? Look carefully where the load is. Whether it is a fully uniformly distributed load, whether it is a partial uniformly distributed load, whether it's a triangular, whether it is a point load, where is the point load? So please look, read carefully, read the tables carefully, okay? Because once you get this wrong, the whole thing is all wrong. And you're not going to get your full marks there, okay? So be very careful. I know some of you are very good at your work, okay? You know how to do it very fast. So because of that speed, okay, you sacrifice on your accuracy. So please be very careful when you're working with especially all these analytical methods, because these are the ones where you cannot afford to be careless. So now that we have established all the preliminary parameters, then we again look at our joints. We have 4 joints, A, B, C, D. Look at our moments. We have 6 members here. Look at the members. We have 6 members. Then you put in your distribution factor and your fixed end moments. Okay, so once you do that, now you release your joints one by one or simultaneously. Okay, in this case, we release it simultaneously. We don't release A. Why? Because it is fixed, so we don't touch it. We don't release D. Why? Also because they are fixed. So we are not going to release joints A and D. We are going to release only joints B and C. So now the minute I release joint B, what happens? I have this unbalanced moment of negative 240. So here I have joint B, and here I have, which part was it? At this side or this side? Yeah. Okay. I have a negative 240. So, okay, I've changed it to anti-clockwise. So this is because I fixed it initially, so that's why I got a 240. Now when I release it, this 240 must be balanced . Okay, this is the unbalanced moment. This unbalanced moment distribute to each member. adjacent member. Okay, I distribute it 50-50. It so happens that these two guys, okay, they share 50% and 50%. Okay, the distribution factor here and here are 0.5 and 0.5, so each one will get 120, 120. Okay, now if I look at joint C, what do I have? Joint C here, I have 240 on this side and 250 on this side. So what is my net unbalanced moment? What is my net? This is my net unbalanced moment. This dotted line here. My net unbalanced moment would be 240, 250 minus 240. So this would be 10 kilonewton meter. So this is my unbalanced moment. I take this unbalanced moment and I distribute it 40%, 60%. That's how I get this 0.4. This 0.4 is actually, this 4 is 0.4 multiplied by 250 minus 240. This gives me 4 kilonewton meter. That's how I get the 4 and 6. Why June? What do you mean by no? June?
No, just ask a question or not, then I say no.
Oh, okay. Okay, sorry. Okay, so I was thinking, why suddenly no? What did I do wrong? Okay, so so here you have, okay, that's how you distribute, that's how you have 4 and 6 here. Okay, we always look at the joint, find the unbalanced moment. So you take the net unbalanced moment in this case here. So then the next one, you look at D. D is fixed, so we are not going to touch this fixed at this moment at all. Let it be fixed. It's already fixed. It would have attracted that much moment. Okay, so we don't want to touch it at all. Now the next, after I have distributed like that, when I lock it back, okay, when I lock back, this part is released. Now I lock. Okay, when I lock it back, what happens? I need to carry over whatever moment that was distributed here to the end, the other end of the member. So this one, member BA had 120. So because A is fixed, I need to transfer 50% over. This is my carry over factor. Okay, I carry over 60 in the same direction to A on the other side, to join A. Okay, then I look at BC. BC has 120. BC, that means I need to carry over to C. Now joint C is locked. So when joint C is locked, that means it is fixed. And if it is fixed, I need to carry over also 50% here. That's how I get the 60 here. 50% of 120 is 60. So similarly with CB. Member CB, I need to look at B. Joint B, I locked it already. So when I lock it, it is fixed. So I need to carry over 50%, which is 2. So same thing with CD. So you go one by one by one. Every member you go. On the same line, you go right across. So when you have CD, you have a moment of 6. You're going to have to carry over to D if D is fixed. So D is fixed, I carry over 50%. So 6 divided by 2 is 3. So now that I have gotten all these moments, carried over, distributed, whatever you are, okay, I have these moments. Now I'm going to release it again. I'm going to release the joints again. And what happens? When I release this joint, I look at every member. I'm not going to release, I already established, I'm not releasing A, I'm not releasing D. I only release B. Now look at B when I release. Look at these two. Okay, When I release here, this is B. I have -1. So I will put 1 here. Okay. And I have -1. Hold on. Wrong. Just give me a minute. Oops. So when I release joint B now, what do I have? I have 2. Okay. I have, where's my eraser student? Okay. So when I release, sorry about that. Okay. When I release joint B, this is my unbalanced moment. Okay. So my unbalanced moment is 2 clockwise. 2. So the equal unbalanced moment is equal to 2. So these 2, I need to distribute it to BA and BC. So I have 50% and 50%. So the counterbalancing moment is in this direction. Okay, so that is why if you look at this direction, this is anti-clockwise, so that's why you have a -1. Okay, -1, -1. Okay, now I look at joint C. Joint C, the unbalanced moment in this case is 60. So this is C. 60 is positive, so this is 60. So the counterbalance would be 60, -60, because this is anti-clockwise. So the counterbalance, you distribute this to 0.6, and this one is 0.4. Okay, that's how you get your distribution of distributed moment. So of course here we don't touch. Then next we lock it back. We lock our joints back so that we can carry over. Here I have -1, I will carry over half of it. Here again I have -1, I carry over to C. Here I have -24, I carry over -12 back to B. Same with this, -36, I carry over -18. Again, now I have locked it back. If I release, my unbalanced moment would be here and here. Okay, this unbalanced moment, again, use your distribution factor. Now always if you look, this is anti-clockwise, your counterbalance will be clockwise. Your unbalanced moment is clockwise, your counterbalance will be anti-clockwise. Okay, so just be very careful. Sometimes students tend to just do it wrongly. The sign is incorrect. So same thing here, -0.5, so you use 0.4 and 0.6. Here you use 0.6. Here you use 0.4. Okay, use your distribution factor. This is distribution factor. So you keep on doing, and then the question is, when do you stop? So you continue until your unbalanced moments are negligible. Now, when you talk about negligible, then the question is, how negligible is negligible? Now, if you look at your moments here from the very beginning here, it's 240, this is in hundreds, right? So you can actually do 3 or 4 times. You look at this unbalanced moment. Now, here is where you have your unbalanced moment, right? This line, distribution line, okay? You look at this, your unbalanced moment, your unbalanced moment is under the CO line. Your unbalanced moment is 0.6, 0.02. You compare with your original one. Is this negligible? Well, you can say, oh yeah, it's negligible. I think it's to me, I think the accuracy is good enough. Then you stop. Okay. So once you stop, then you have to add up all the moments vertically. So when you add up the moments, these moments will be your internal moments. Of course, if you had stopped somewhere here, let's say you stop somewhere here, you find that your moments, the adding up of the moments will be different from the guy who did another 2 rounds of iteration. And then you keep on, let's say another more, another student do another 2 more iterations. You find that your accuracy here, your moment here will become more and more, you will see that it becomes more and more accurate. So the more iterations you do, the more accurate it becomes. So the question is, as an engineer, you have to decide, right, how accurate you want, number one, and whether you the level of accuracy that you want. So it is actually a question of judgment. Okay, if let's say your intention now is to really carry out a detailed analysis, then of course you want it to be very accurate. But if let's say your intent is only to like counter check, okay, to counter check the computer output, then of course you don't really need to go into so high a level of accuracy, right? You get in the range, and it's within that range of, let's say in this case, 62, 125, 280. Then you say, yeah, I think it's good enough. Then you check, yeah, it's okay. So the computer output is okay. So it really depends on your intent. But for our course, I would suggest that you try to do until such a time that this one, compared to the original FEM, it's quite negligible. Okay. So normally for students, I mean, when I was a student, what I used to do is, because girls being girls, we tend to be a little bit more cautious. So we do a little bit, few more times long, So, but it's really up to you. Like I said, as long as you get within that range, and you really understand how to do the principles behind this balancing of the or rather the distribution of the unbalanced moments, then I think you have achieved the course outcome of knowing how to analyze beams using this method. Okay, so then after that, of course, the last part, we digress a little. Sum up your resulting moments. So the resulting moments here are basically, when we talk about resulting moments here, these are your internal moments. Okay, so be very careful. These moments that you get, they are not the so-called external moments. These are the internal moments. You don't get external. External moments are normally those moments that you apply onto the structure. Internal are what happens when you apply loads onto the structure, and how the structure actually reacts to these load applications. Okay, so these are your internal moments. So the last step, of course, this is the part where you need to calculate all the end shears. You need to use your equations of equilibrium, get your end shears, your bending moment diagram. Okay, so I'm not going to run through this part, because these are actually already back to the part where everything is statically determinate, in the sense, and you can actually apply normal equations of equilibrium to your structure. Okay, and then okay, this is the other member AB, member B. Excuse me. This is member AB, this is member BC, and this is member CD. Okay, I've split it one by one to show you, so that the reason why I show you guys all in detail is for you to go back and try to get all these values. Okay, if you can't get these values, go either, like I said earlier, ask your friends, or come and ask any one of us. There are 3 of us. You guys are pretty lucky that you have 3 of us this time. Okay. So you choose whichever lecturer that you feel comfortable with, and then you go and approach them. No problem. This is basic shear force and bending moment. Okay, so what I have done now here is I have combined all the internal moments. So the black arrows here, oh, everything is black. The curved black arrows here are the internal moments. The vertical values here, the vertical arrows here are showing you all the internal shear, right? These are the internal shear, and of course this part here, the red ones are your support moments. Okay, so from here you look at your shear force diagram first. Look at this downward 15.6, no loads here, so this shear remains the same. Then you go up to 100 and is it 107? Yeah, 107. Okay, then because of the loads here, these loads will be pushing your shear force diagram down this way until 133, and then shear on the other side is 139, and then this again, there are no loads, so it's flat all the way. Then you have a point load that pushes it down 250, so these two add up is actually 250. Then this one is 119. Okay, so this is how you draw your shear force diagram, and of course you follow it with your bending moment diagram. Okay, some people, they like to do the bending moment diagram first because you have your internal moments already. So once you have your internal moments, right, you know how to draw your bending moment diagram, and then you can draw your bending moment diagram first, and then you can work with. But it really depends on the individual preference. Okay, once you have gotten more practice, then you may want to start with the shear force diagram first. Okay, so with that, why don't we take a break of maybe 10 minutes, and then I will come back. I will be showing you some modification to the stiffness factors for those of you who you already understand the basic concept. I will run through the modified stiffness factors, and then after that, maybe the last half an hour of the second part, we will go into the frames with no swing. Okay, so if you have any questions, just post it during the break, and I will get back to you after the break. We will take a 10-minute break. We'll be back by 9:03. Is it 9:05? We'll take 9:05. Okay, 7 minutes. 9:05. We'll be back. And meanwhile, please remember to check your attendance and make sure that your name is marked as present. Okay. Okay, we are back. 9:05. Okay, so now that you know how to calculate or analyze continuous beams using where your phi n is fixed and all that, so you know how to find the member stiffness, calculate the distribution factor, and so on and so forth. So the stiffness factor, the member stiffness factor, if what you have learned is that if the phi n is fixed, you use 4 EI over L, and if it's phi n pin, you use 3 EI over L. But what I did not show you is why you get your 4 EI over 3 EI over L, because I just told you earlier on in the lecture, if it's fixed, you can actually get 4 EI over L based on the slope deflection criteria that we have established earlier. So anyway, I just want to run through so that you understand how you get the 3 EI over L as well. So the 3 EI over L is actually a modified stiffness factor. Because what we did was, when we first derived all our slope deflection equation, we also assumed the phi n to be fixed. So if, let's say, the phi n is pin, right? So if the phi n now is pin and I apply a moment of MAB here. So this is my applied moment. Okay, my applied moment is MAB. What would happen is, if you apply a moment here, joint A will rotate, right? It will rotate by an angle of theta. So how are we going to find out how much of this rotation? Because why? We already established that stiffness, right, is related to somehow, okay, somehow, oh sorry, what is this? It is somehow, okay, it is related to your rotation, remember? The amount of moment needed to rotate the beam or the joint by an amount of theta is what you call stiffness. So if the phi n is pin, right? If the phi n is pin, what we are going to do is we are going to use the conjugate beam method to establish, right, the value of theta, or the relationship between the moment and the theta. Okay, so here I unlock the joint of AB. So that means when I unlock the joint, it means I apply a moment of M. What would happen is that I need to find out what is this. Now, if you look at this, unless you use other methods like other analytical method that you've learned earlier, either the force method, the virtual work method, and all that, we are using the conjugate beam method to establish this. To do that, what I need to do is I need to find the moment, the bending moment here in the real beam. So the bending moment I establish is like that. Okay, this is my moment M. So when I convert it to a conjugate beam, I will call this A prime, and this is B prime. I will convert the fixity at the joints, and since this is pin and pin, so this remains pin and pin. Okay, so there's no change in the fixity. The moment now, if I divide by EI, becomes the load on the conjugate beam, and because this is positive, the loads are pointing upwards. I hope you recall how to do your conjugate beam. Okay, now we know that from the conjugate beam method, the theta in the real beam, or the slope this is the slope, right, or rotation, they call it slope or rotation. this in the real beam is equivalent to what? Is numerically equal to your shear in the conjugate beam. Okay, so here, if I'm using the conjugate beam method, if I have this load, applied load on the beam, I should be able to find the shear at this point, because the shear here, VA prime, is numerically equal to my theta in the real beam. Okay, so here, if I apply my normal equilibrium equations, I will be able to find what is VA. So if I take summation of moment about MB prime, in this case, this is MB prime. So I would have this equation and I can solve for VA. Okay, V prime A or VA prime is equal to ML over 3EI. So here, based on the conjugate beam, because it is numerically equal to the slope theta, so I say theta is equal to this. And I rearrange the equation to get M in terms of theta, I will have this. And this is the constant K. Okay, M is proportional to theta, so therefore this is the coefficient for the stiffness, K. So that is how we show that if your far end, if the far end of your member is a pin or roller support, then the factor that you can modify it to will be this. This is the K for far end pin. So that's why initially, earlier on, we were using either 4EI over L or 3EI over L. So this was the modified one. But of course, this is only the two very simple ones that I would suggest that you remember. The rest, if you don't want to remember, that's really up to you. But it would help you if you, let's say you are, you join a very small firm and they do not have any engineering software, then you need to use moment distribution. Then the subsequent stiffness factors will help you a lot. Okay, why? Because the next one, if let's say you have a symmetrical beam with loading, that means you have a symmetrical beam and you have symmetrical loading. Okay, sometimes we do get this in real life. Okay, so if you have symmetrical beam and symmetrical loading, how do you mean by symmetrical? It means the whole thing is symmetrical. If I draw a axis of symmetry here, both sides are symmetrical. So if I do that, then what happens? I can actually modify my K factor. How do I do that? I will take this free body diagram, okay, and then I change from the real beam, I change it to the conjugate beam. So remember here, it is internal. These are internal hinges or internal pin. Then when you convert, it becomes internal. This become a hinge. Okay, these are pin. Then this one becomes a hinge. So if they are hinged, then you know your moment here is 0, right? So when the moment is 0, that means you only have the shear forces on both sides. And of course, don't forget your load, because your load here, from the real beam, you should be able to establish the moment in this beam. Okay, the moment here. The moment here you found that this moment is like that. Okay, it is negative. So this moment you divide by EI, right? So your moment was actually ML. So you divide by EI, so you get ML over EI. Taking summation of moments, you should be able to establish your VB prime. And VB prime, we already said, this is equal to the theta or the slope in the real beam. That is how you get the equation of M equals to 2EI over L theta. So if I look at this K value here, remember we already said M is equal to K theta, so K is equal to 2EI over L. So if you have a beam that is symmetrical in geometry and symmetrical in loading, you can also have something like this. It doesn't matter. Symmetrical in geometry. Geometry means all these are the same. That means this is L1, this is L1, or this can be L2. You can have a load here only. This is also symmetrical in loading. So it really depends on what kind of structure, as long as they are symmetrical in geometry or symmetrical in loading. You can also have something like this. Okay, this is also symmetrical in geometry if the geometries are all the same, right? Fixity same, support condition same, dimension same, so they are symmetrical in geometry, symmetrical in loading. Okay, so you can actually use this modified equation, and when you use this, you only need to do the moment distribution for half the beam. So you just imagine, when you do moment distribution for half the beam, you're only doing 1, 2 joints. Here you have to do 4 joints, you see. So that's the beauty of this using the modified equation. But to me, I think for at your level, since this is only year 2, you're not going to the advanced classes. Maybe if you do not want to use these modified factors, that's okay. Okay, you can still maintain the basic factors, which is 4EI over L or 3EI over L, and you just analyze for the whole. A bit slow, but you know, you get there. Okay, it doesn't really matter as long as you understand the concept. So when let's say you become more proficient in doing this, then maybe you want to use the modified equation. It's really up to you. Okay. Other one is the symmetrical beam. That means the beam is symmetrical in geometry, but the loadings are anti-symmetrical. That means if I draw the axis of symmetry here, the loadings are upside down. Okay, so again, we use the conjugate beam. We establish the moment for this area here, for this span. You establish the moment, you divide by EI. So in this case, you have M over EI here and M over EI here. Okay, then you calculate to find your VB prime. Once you get your VB prime, this is your theta, then you find that the modified factor is 6EI over L. Okay, so if you really want to do this again, same thing, we are only doing half the beam instead of doing the full beam. But if you're using this, only if you're using this. If you're using the traditional of 4EI over L, or the 3EI over, in this case just 4EI over L, then you need to do for all the joints, okay, A, B, C, and D. Okay, don't do halfway. Halfway you cannot use 4EI over L. Okay. Any questions so far? If you can't catch it, if you want the wordings and all that, I think Hibler will explain quite well in the book. Of course, I think he has also some exercises where he uses this modified one. But if you do not want, what you can do is you can do the long method and have a good practice on the on learning how to use the method. So to sum up, for beam analysis, okay, we of course we need to identify, first and foremost, you identify what are the joints on the beam. You calculate the stiffness factors for each span at the joints. Now, after you have calculated the member stiffness, okay, please don't forget. Sometimes I forget to write this. Okay, member stiffness. Then you determine the distribution factors. So of course here, I forgot to also mention again and again, I need to do it again and again. So your 4EI over L, this is for far end fixed. And you also have 3EI over L, which is far end pin. Okay, so these are the two member stiffnesses that I will normally work with because I'm basing for the majority of the class. So for those of you who want to use, you can also do the modified stiffness factors. Okay, it's really up to you. But these are the two that you need to really know. Then after that, you determine your distribution factor, which is the ratio of the stiffness, the member stiffness over the sum of all the stiffnesses at the joints. So as usual, here if you want to memorize it, if not, you just use by logic, you will find that your distribution factor for the far if the far end is fixed end, then it's 0. If it's pin or roller, it's 1. Then after that, you look for your fixed end moments. Fixed end moments will only occur if your span is loaded or loads are applied along the span. If the loads are applied at the joints, then there is no fixed end moments. So of course, we work on the sign convention. So this is your sign convention. Don't forget. Always we take clockwise as positive. Okay. And then you tabulate all your values. The tabulation, of course, you start with your joint. Joint, member, right? Distribution factor, FEM. These are the main ones that you really need to make sure. And then after that, you go on. Once you finish your FEM, then remember, you get your FEM, you will need to release it. Okay, you assume that to get your FEM, you assume all the joints, right, at which the moments must be determined, you lock it. So that is why all our internal joints are locked. Then you determine the moment that you need to put each joint in equilibrium. This is the part where you're actually releasing it. Okay, so you release and unlock the joints, you distribute it to each and every member of each and every member that is connected to the joint. Then you carry over. When you carry over, you need to lock back. Okay, this is where you lock back. And then you carry over the moments and make sure that the carryover factor is this only if the other end is fixed. If the other end is a pin or roller, please don't carry over. Okay, then you repeat lock, unlock, lock, unlock until your unbalanced moments are negligible. And then you add the moments up vertically so that you can determine all the internal moments. Okay? So any questions so far? Because once you understand this moment distribution, the frames should be no problem for you. The only thing is there's a slight difference in the swaying frames only. No questions, Okay, if no questions, then we will proceed on to frames. So of course, like slope deflection, you need to establish whether the frame sway or has no side sway. Okay, so that's the only difference between the beams and the frame. If you see a frame, you need to first and foremost establish whether it has a side sway or not. And how do we know whether it has a side sway? There are only two conditions. One, you must make sure that the frame is properly restrained. And two, you make sure that the loads are symmetrical. Then you have no side sway. Either one. If it is restrained, even if you have non-symmetrical loading, that's okay. It will not sway. But if it is not restrained, and you also have that unsymmetrical loading, then definitely it will have a side sway. Okay, so this one sometimes it takes time for you to establish to see how, because you really need to understand how the structure will work. Okay, how the structure will work, how it behaves under the load. So try to spend some time, right, drawing. Take the frame, and then you put some loads there, and then you see how it bends and all that. And if you're not very sure, you can take something flexible like your ruler, something that is flexible, fix it, press it hard to sort of simulate a fixed end. Maybe you put a roller, you make a joint to establish something that you can rotate about the joint, and then you see how the structure works. Okay, try to do that so that you can have a feel of the structure. It works quite well. Well, at least for me, sometimes I do not know how the structure works. Then I will try to find something flexible, and I will try to put it and see. You know, you just have to imagine a bit. So this is how you learn. Of course, there are some people who will get it very quickly, but I am a little bit slow in that sense. So I need all these so-called tools to help me understand the behavior. It will take some time. Some engineers, even like after 2-3 years, you know, then only they get the hang of the behavior. But it is okay. These are all part and parcel of your learning journey as an engineer. Okay. So anyway, I digress. So let's go on to example 5. Determine the internal moments at the joints of the frame as shown. So there is a pin at E and D. So these two, E and D, are actually pinned connections, and A is a fixed connection. Okay, so if I were to draw just a simple line diagram or a schematic diagram, I can actually draw something like this. Pin, oh sorry, pin, oh, pin, and this is fixed. Okay, I can draw something like this. I put my load here, and I put my load here, 35, 60. Okay, this is, you can draw it like that if you want a line, a schematic diagram. So anyway, what do we know about the structure? First, because it is a frame, we need to establish whether there is a side sway. So you look at this diagram, look at all the joints, because you can only restrain the structure at the joints, right? At the supports. So look at this support, look at this support, and look at this support. It is restrained here. It is restrained here in this direction and this direction. It is restrained here in this direction and this direction, right? This one is here, here, here. Now, please bear with me. Sometimes I don't really bother about the directions here, because this is just to establish what are the forces there. If you want, you can just make sure that it's in the correct direction. But in this case, it doesn't. Just bear with me. I will just indicate these are the forces there. It may not be in the correct direction. It may or may not be in the correct direction. Okay, so just bear with me. So anyway, so you have all these. These are all restrained. Why? You will say, how come this is not fixed? So this is not restrained. Now look at this. You only have a load. What causes the side sway? Side sway is left to right, right? So here, it cannot move left to right. It's already fixed, right? It cannot move left. Why? Because your member is not extensible. It is flexible, but it's not extensible. It cannot elongate, right? Unless it says, yeah, the members can elongate, then it's different, right? Like in topic 1, we say the wire is extensible, then you have your delta, right? But in this case, we say that the members are inextensible, so they are rigid members in the sense, sorry, not rigid members, they are inextensible members, so you cannot extend this way, so it's not going to move this way. And is it going to move this way? It can't, because why? Because I already have a restraint here. Okay, so from looking at this structure, I know that it is not going to sway. So first and foremost, I established this frame has no side sway. Okay, so no side sway means I can just analyze, right? Because earlier on we said you carry out your moment distribution as similar for beams. So now if I have no side sway, I will just carry on my analysis as though it is a beam. So individual members, right? The beam, we took it as individual members. So similar with this, we are taking AB, BC, CD, and CE. We are taking individual members to analyze. And then next, we need to also look at the FEM. Now look at this force here. This force is applied at the joint, right? This force is applied at joint B. So there will be no fixed end moment here because it is applied at the joint. So it's not going to create any fixed end moments here or here, right? So as far as this is concerned, there is no fixed end moment here. Right? There's no fixed end, there's no fixed end. Maybe I should draw outside. Okay, never mind. So then here, I have a load on the beam. So definitely I will have FEMBC and I will have FEMBCB. Okay? For the rest of it, there are no more loads, so there will be no fixed end moment. So you know that these are the things that you know about the structure. Okay, so the first thing, remember, what was the first thing that we need to do when we are doing our moment distribution? It is to find our member stiffness. So in this case, you need to look at each and every member. So maybe we just draw the member here. Yeah, I always fix it. Okay, so this is A, B, C, D, and B. Okay, so if I look at joint A is fixed. So my KAB would be, joint A is fixed, joint B is also fixed. Remember, all the internal here, this one we will fix, this one we will fix. Okay, so we will lock them temporarily. So your KAB is 4EI over L. So joint B is rigid. Well, we normally we refer to all the joints as rigid unless we specify differently. So when they are rigid, that means it rotates as one. Okay, so when this joint B rotates, it rotates here. The angle of rotation here and here, they would be the same. Okay, so that's why we call it rigid. So for joint B, I will have KBA. Now KBA, if I look at A is fixed, so I use 4 also. For BC, KBC, same thing, 4. Joint C, again, same thing. Now look at joint C. I have 3 members. So I will have KCB, KCD, and KCE. Now, if I look at KCB, B is fixed, so that's why I have 4. But if I look at KCD, D is pin. And remember, far end pin, I will use 3. When I look at KCE, E is pin. So again, I use 3. Okay, that's how you establish your member stiffness here. Then you look at joint D. Joint D is pin, but you're looking at KDC. You're looking at C here. C is also rigid, so therefore you use 4. Same with E. For KEC, C is fixed, so you have 4. Okay, that's how you start. I think this one you should have no problem. From topic 2 until now, you have already worked on this, so you should have no problem with this. Next, the distribution factor. So distribution factor, same thing. Wall will be 0. BA, you look at your B and your C. BA and BC. So this is BA. This is BC. Okay, so just fill in all the ratios there. So once you have done that, CB, joint C and joint D. Now, DC and EC, because they are pinned, so your distribution factor is 1. Then you have your fixed end moment. Your fixed end moment, as I said earlier, the point load of 60 kilonewton does not help, does not contribute to any fixed end moment, so we ignore it. What you will have is only the at member BC. Okay, so again, we follow back the same sign convention. We are using positive as clockwise, so we will follow back this one. How do I get rid of this? This one always comes up. Is this the one? Okay. Oh, what happened? Okay. So now we have everything. We have all our parameters. We have our joints. We have our member. We have our distribution factor. Now, one way to counter check your distribution factor, the summation of the distribution factor, summation of your distribution factor at any joint, okay, must be equal to 1. So if you look at joint B, the distribution factor between BA and BC, these two is equal to 1. So you're safe. Same with this. At C, you have this plus this plus this. They are all equal to 1. So you know you're okay. Okay? So that is one way to just counter check at this stage. One thing bad about this moment distribution method is that it is very, in a way, all these are mathematical only, right? It's no complicated or no complex equations or anything like that. Just pure addition, subtraction, division. These are all arithmetics. But it is very tedious. And if you make a mistake, you will find that at the end of it here, oh, how come it doesn't balance, So for those of you who did maybe accounting in Form 4, Form 5, you'll find that, you need to balance your balance sheets and all that. And suddenly you work all the way to the last entry and you find that it doesn't balance. So same thing with this. Okay. So anyway, we digress again. So FEM, okay, FEM, you will find that you have FEM on BC and CB. That's the only member that had loadings. Okay. Now, once you have this, you're going to unlock the joints. Here, you're going to release or unlock your joints. Okay, this is unlocking part. A is fixed, you don't unlock. D is pin. This is pin. You will notice that there was nothing here, so we left it as blank. Okay. So here, when I unlock here, look at joint B, I will unlock joint B. The unbalanced moment is 135, right? Because this is negative 135, so the unbalance would be it must have an equal and opposite magnitude as this, equal and opposite moment as this. So I will distribute, okay, among the member of BA and BC using 0.54. So here I will have 0.545 multiplied by 135. That's how I get this value here. Okay, because I have joint B. When I release this, this is 135. Okay, I release it, I will have an equal and opposite. This is the counterbalance moment. And this counterbalance moment, I will distribute it to BA, and I will distribute it to BC. And here I have 0.545 multiplied by 135. That gives me 73.6. This one is 455 multiplied by 135. This gives me 61.4. Okay, I will just show you one, and then the rest is all the same. So here you have that. Now, when you look at joint C, same thing. Now, joint C is slightly different in the sense that joint C, you have 3 members, right? So here you have 135 as CB. This is CB. So 135 is here, right? So how much is the counterbalance? Also 135. Now this 135, you must share it among this, and among this, right? Individually, right? 135, you unlock it, you will sort of move all to the 3 members. So these 3 members, how do you get it? You use your 0.33 multiplied there, this one multiplied there, this one multiplied there. Okay, that's how you balance it so that you get an equal and this counterbalance of 135. And because this is in anti-clockwise, so that's why all your values here are negative. Okay, after you've done that, happy you have distributed to all the members. Now you lock it back. Okay, time to close the shop. You lock it. And when you lock it, you look at here, you have 73.6 at BA, you look at A. A is fixed, so you need to carry over 50%. Okay? Then you look at BC, you got 61.4. C, is it fixed? Yeah, so here again, carry over 50%. Look at B here, CB, so you're looking at B. B is also fixed, so you need to carry over negative 44.6 over here, so it's negative 22.3. Look at D, CD, right? CD. So D, is it fixed or pin? Pin. So you're not going to touch it. You're not going to take this and put here. Okay. This one is not. You don't carry over here. Okay. You don't carry over because D is pin. It's not going to attract any any moment at all. So why do you want to carry over? It's not attracting any moment, right? So there is no moment here. So same with CE. You're not going to carry over to E because there is no, this is pin. So these two, there is no carry over. Only 1, 2, 3 you carry over. So same thing, distribution here, when you unlock. When you unlock, where's your unbalanced moment? This one? No, because this is fixed, so you leave it here. Don't touch it. You unlock B, you have negative 22.3 now. So your B now is negative 22.3. So this is on BC, so BC is here. This is 22.3. So I need to have a counter moment of 22.3. But this counter moment, I need to distribute to here and to here. So I have my distributed to BA and distributed to BC. Okay, so that's how I have my 22.3. I will multiply again by 0.545 to get 12.2. And I multiply by 0.455 to get my 10.1. Okay, that's how you get these two. So this one, you will have 0.545 multiplied by 22.3. You should get how much? 12.2. Okay, that's how you get your moment here, 12.2. And so on. So same with C. C is 30.7. Now it's in the clockwise, so you have to do it counterclockwise. So that's why you have all the negative values. And then when you lock it back, okay, sometimes the reason why we draw this line is to say, oh, we are going to lock it back. And when you lock it back, that's when you carry over. So here, 12.2, my A is fixed again, 50% here, right? BC again 50%, CB again 50%. Now you look at this moment now, 6.1, 5.1, 5.1. Do you think you can stop your iteration here? I don't think so, because 5 kilonewton meter, I think it's still quite big. Okay, your unbalanced moment is still not negligible. So you need to do another round of locking and unlocking. So you lock, unlock again, you get another unbalanced moment here. 1.4, 0.8, 1.2. To you, maybe it's still big. Then we try again, another round. Okay? Once you do another round, you get this 0.2, 0.2, 0.2 like that. And then if you don't want to do, you still want to do another round, that's okay. Just do another round. You see what happens to this. Now, what I suggest you to do is now, with this, you do another round and another round, and you see whether it helps or not. Then you will know when you can actually stop. Okay, it gives you a feel and a level of confidence when you do another problem on your own. Okay, try to go down, and you see how much more accurate you will get. Okay, you may not, it's very unlikely you will get anything very far from these values, but try it and see. If let's say I do another round, see what happens. You do another round, see what happens. Then you say, oh yeah, I think to to one decimal place, not much difference. So you maintain it. Then you know next time during your exam or during any problem solving on your own, then you can try, okay, I think I can stop here and I should be able to get the kind of accuracy that I'm looking for. Okay, that is one way of advising you guys when to stop, because every semester students will ask me, when do I stop? So the only way I think you can do it is by practicing on your own, and you see the kind of accuracy. Okay. For the exam, I would not expect you all to go into like two decimal places or 3 decimal places and so on for the internal moments anyway. Okay, so if you want to work to 1 decimal place or 2, then sometimes I will write down there in the question. So please read the question carefully. Okay, so once we have done that, we have established these are all the internal moments of each joint, okay, or of each n member of the joint, well, at each joint. Okay. Then what I want you to do is, again, homework, okay, please go and work on this shear force. I already show you the bending moment. If you want, you translate from here, translate to here, okay. Then you see whether you can get this. Also try to get this. Now I have skipped one step where I show you how to get your end shears. Okay, so what you do is you have your member AB. This is your member AB. If you don't want to draw like that, you just draw A, B, and of course, oh, sorry, this is the frame. Your member, this is AB. Okay, so you draw your member AB. You indicate all the AX, AY, of course you have MA, right? And then you have the load here, 60 kilonewton. Then here you would have another By, and then you also have your Bx, right? Because this is a frame, so you need to have 3 degrees of freedom. Then from here, you can calculate all the values. Now, for frame, this one, you may not be able to calculate all the values at one shot. So after you've calculated this value, maybe you look at the structure as a whole, okay? Once you establish one of the forces, you can actually get, then you look at the other end of it, you know, one member at a time, and then you look at the entire structure. Okay. Once you have found the internal moments, guys, once you have found the internal moments, you will find that all these unknowns you can actually establish, because once you get your internal moment here, this you can establish it. You know this moment. Once you know this moment, how many unknowns do you still have? 1, 2, 3, 4, 5, 6, right? So 6 unknowns, but if you break them down, you can again find another unknown. Break it down, you can find another unknown, and so on. So then you can find all the support reactions in the beam, in the frame. Okay, and then you can come up to your shear force and bending moment time. So that's why I purposely did not show you this, because I would like you guys to go back and try it. Okay, what you can do is, I want to see, this is a homework, because it will also help you in your test. So I want you all to come up with it, and then what you do is, let me show you something. We are going to do something like this. Where am I? Yes, here. Okay, so what happened is this. Here, okay, under class notebook, okay, go to your class notebook. Yeah, how many of you guys are? I think 100 of you. Okay, what I need you to do is, what I need you to do is, you will find that on your class notebook, you will have a class notebook here. When you submit it, what you submit to me, it will appear in your own name, under your own name. For me, I can access each and every student here. Okay, all of you, your names are here. So when you submit into the class notebook here, your own class notebook, submit what I want you to do is submit the step between here to here. Okay, submit here, show me your working, submit it down here. Let's say Ko Yong Wei. Okay, you submit here, it should appear inside here. Okay, inside your class notes here, you can actually put in your drawing, your everything down there. Okay, submit it here. You can also insert, let's say you're fine with drawing just by hand, okay, but you don't have a tablet, that's okay. You draw it on a piece of paper, you save it as a PDF, like as though you're going for your exam, and then you just upload inside here. Okay, you just put file, not this one. So you just go inside here, you put file. Okay, sorry. Let me see. Insert, okay. You can insert file printout. So once you insert file printout, it will come onto your folder. So what I need all of you to do is, as a homework, okay, I will give you time until our next class. I want to see all of you submitting into your own notebook, and I'm going to check. I'm going to see who will do your homework. Okay, this is a homework. This is not a tutorial. I need you all to do this. Okay, you show me the working between here, from here, getting your internal moments, find your end shears, and then draw your shear force diagram. Okay, that is what I want to see. Any questions so far? Anyone don't understand what I want? So I will also be able to check those of you who actually attend my class and listen to me, and also those who don't listen, don't attend, but name is here. Okay. Now, normally we will not. I mean, we know that if you don't want to listen, that's okay. But I want all of you to do the homework. So I hope that those of you whose name is present, but you are physically not present, please go back and listen to the recording and go and do the homework. And I want to see it by Thursday. So by Thursday, 2 o'clock, I would have checked everyone, see who has not submitted. Okay? I'll give you 2 days to do it. So if there are no further questions, I think we shall call it a day. I will not start with the next. I think the next topic would be the last topic of the moment distribution. Okay, so I will finish that, and then I hope that I will be able to introduce a little bit on the assignment, so that some of you may want to start. Oh, there are quite a fair bit tomorrow. So I mean, if I cannot finish the topic itself, then maybe after the test, I will be briefing you on the assignment in week 9, Thursday. Okay, but I should be uploading the assignments by today or tomorrow, so that you can actually start working and see how much to do. I will upload both the assignments. Okay, now the whole idea is for you to upload to do the assignment part by part. Don't go and leave it until the end, because both of the assignments have the same deadline. Do it now, finish it, and get it over and done with. Okay, and then if you want, you can submit. And I believe it's the same thing. You can bring into your groups. I will try to upload it today, so that you know how to sort out your groups as well. Okay, so if there's no questions today, then we shall call it the day. I will see you on Thursday then. Thank you.